In this video, we're going to talk about how to solve two specific problems in mathematics, namely what we're going to call the area problem and the distance problem. Now these are pretty closely related to each other, so we're going to focus on the idea of area first. So what we want to do is we want to find the area of a region S below a curve y equals f of x from points A to B. So graphically what we're doing is we've got some function here, and we've got some point A over here and some point B over here, and we've got this curve, and what we want to do is we want to figure out the area of the region between these. So in other words, we're just trying to figure out what is this area that I am shading in blue. That's the question that we want to answer. Now, to help us with this, we're going to think about how do we compute areas usually. And so there are a few ways that we know how to compute areas. If you have a rectangle with length L and width W, the area is just length times width. We know if we have a triangle with base B and height h, that the area is given by 1/2 base times height. But one other trick that you may or may not remember is that if you have a more complicated shape, say we have the following shape, the way we can compute its area is we can break it up into pieces. And so we break it up to this rectangle and this triangle, and then we just find the full area by adding up the area of the two pieces. And so that's the idea that we're going to use to find the area of this more complicated region. What we're going to do is we're going to break it up into pieces and find the area of each piece, and then add them all up. And so if we have some region, we're just going to break it up into pieces. Area 1, 2, 3, 4, 5, and 6. And then the sum of the 6 areas would be the whole area. So A1 is A1 plus A2, and so on up to A6. And now this makes a lot of sense. This would give us the area. But the problem is we don't really know how to compute these areas either. But notice they're kind of close to rectangles. That if we just kind of fill in gaps or cut off pieces, we can just make a bunch of rectangles. We can make 6 rectangles here. And they aren't quite the right area, but they're close. And so if we use these 6 rectangles, we can approximate the areas of A1, A2 through A6. And then add those up, and we get an approximation for the actual area. And so when we use this idea now to compute an actual example, but it's just this idea of we're going to break it up into pieces, approximate those pieces with rectangles, add up the areas of the rectangles to get an approximation. Okay. And so what we're going to do in this example is we're going to approximate the area under the parabola y equals x squared from 0 to 1 using 4 rectangles. Okay, and so if we draw this picture, the graph of y equals x squared looks something like the following. And we're going to say 1 is right here, and then 0 is obviously over here. And so we're trying to approximate this area in blue. And so the way we're going to do it is we're going to use 4 rectangles. So we're going to first take this region and break it up into 4 strips. And so we have 0 here, 1/4 here, 1/2, 3/4, and then 1. And we're just going to break it up into these 4 strips. So we have S1, S2, S3, and S4. And we're going to approximate each of those strips using a rectangle. Because we know the area of rectangles, we don't know the area of each of these strips. And so doing that, we have 0, 1/4, 1/2, 3/4, and 1. So what we're going to do is we're just going to use the right side of each of these regions to form a rectangle. So first rectangle is going to be this one, second rectangle, third rectangle, and fourth rectangle. And so we're just using the right side of each of these intervals that we've set up to form our rectangles. There's nothing special about using the right side, it's just the way I'm drawing it. This one, we're going to use the left side in a second. So these are our 4 rectangles, and we can find the area of each of these rectangles fairly easily. Notice that each of these rectangles has a base of 1/4. So each has base 1/4, and then its height is given by the value of the function at that point. And so the height at the 1/4 point is just 1/4 squared, and so on. And now we're going to add all of these areas up. So actually, let's write the areas down first. This would be 1/4 times 1/4 squared, 1/4 times 1/2 squared, 1/4 times 3/4 squared, and then 1/4 times 1 squared. And we're going to add all of these up to get the approximation area. And we're going to call this R4, just because we're using the right side of each interval for the approximation. We're just going to write R4 for that. And so we have 1/4 plus 1/4 squared plus 1/4. Sorry, it's 1/4 times 1/4 squared. 1/4 times 1/2 squared plus 1/4 times 3/4 squared plus 1/4 times 1 squared. Now if we add all of these up, you can compute this as approximately 0.46875. So that gives us an idea of the area. That's not the actual areas. We can see that we very clearly have overestimated the area, but it gives us an idea. It gives us a range of what the area is. And now, like I said, there's nothing special about using the right-hand side. And so, I didn't write this down, but this is actually 15/32 if you compute the actual number. And so now let's do the left-hand side. So now we're just going to use the left-hand side of each interval instead of the right-hand side to form our rectangles. So again, we have our region. We have 0, 1/4, 1/2, 3/4, and then 1. And now to form our rectangles, we're going to use the left side instead of the right side. So the first rectangle has a height of 0. Then our second rectangle, third rectangle, and fourth rectangle. And so, again, each of these bases is 1/4. So we have 1/4 So for the first rectangle, we have 1/4 the base times the height, which is 0 squared, 1/4 times 1/4 squared, 1/4 times 1/2 squared, and 1/4 times 3/4 squared. And again, we're getting the heights just by plugging them into the function y equals x squared. And now we're going to add all these up to get another approximation. And so since we use the left side, we're going to call this L4. And so we have 1/4 times 0 plus 1/4 times 1/4 squared plus 1/4 times 1/2 squared plus 1/4 times 3/4 squared. And this is equal to 7/32, which is approximately 0.21875. And so what we found here is this is clearly an underestimate, but we found the actual area is going to be somewhere in between. So it falls between what we did on the right-hand side and what we did on the left-hand side. And so the actual area is between 17/32, 15/32, and 7/32. Which gives us a better idea than we had before. We know it's somewhere between 0.21875 and 46875, which is more information than we had before. But the thing is there's nothing special about picking 4 rectangles. We could have broken it up into 10 sections, 20 sections, 1,000 sections. Like, the number of sections we break it into just makes more things to add up, but we can still do it. We can still find the area of each rectangle and add them up. And when you do that, you get an interesting situation. So we're going to let n be the number of rectangles, and then Ln is going to be the sum if we use all left endpoints, and Rn is if we use all right endpoints. So just like we did before, Ln corresponds to the second one where we pick the left side of each of the things we're breaking up into, and then add them up. And then Rn is when we use the right side. And again, n, this is the number of rectangles. Okay? And so if we used 10 rectangles, we get 0.2850 for the left-hand side, and we get 0.385 for the right-hand side. If we use 20 rectangles, we get 0.30875 for the left-hand side, 0.35875 for the right-hand side. If we use 50 rectangles, we get 0.31685 for the left-hand side, and 0.3434 for the right-hand side. And if we use 1,000 rectangles, we get 0.33283 for the left-hand side, and 0.33383 from the right-hand side. And so notice what is happening here. As we use more and more rectangles, we seem to be zeroing in on a value. And so this is the idea of a limit. We've seen this idea before. And so it seems like these two things actually are going to have the same limit. It looks like it's about 0.333 or something like that. So it looks kind of like we're going towards 1/3. And so both of them, though, seem like that is what they're doing. And that is kind of the idea behind finding areas, is that this left-hand side and right-hand side both go towards the same thing, and that is what our area is going to then be. So the actual area we suspect is 1/3. And so let's do this in a bit more generality now. And so we're going to apply the same idea, like using more and more rectangles, to an arbitrary surface, or an arbitrary shape. So we have the following setup. So we want to go from A to B, and we're going to divide this up into pieces, Now we're going to divide it up into n pieces, which n is an arbitrary number, so I can't draw that obviously, so I'm just going to put a bunch of dots. So S1, S2, S3, S4, a bunch of dots, Sn minus 1, and then Sn. So we divided up, Sn minus 2, Sn minus 1, and then Sn. So we've divided it up into n pieces. This is A, we're going to call this x1, x2, x3, x4, xn minus 3, xn minus 2, xn minus 1, and then B is the same as xn. And so we have these n pieces, these n strips that we've divided it up into. Each of them will have equal width, and so we were taking the interval A to B, and so the overall width here, they all have the same number, we have n of them. So in B minus A, that's the width of the whole interval, but we're dividing up into n pieces. And so this is going to be the width of each rectangle. That's the width of each of these pieces that we've made. Now these intervals we're taking are literally x0, which is A. So I'll write A to x1, x1 to x2, and so on, xn minus 2 to xn minus 1, and then xn minus 1 to b. And so we have n of these intervals that we've divided it up into, each of which has a length of b minus a over n. And so if we want to figure out what these x sub i's are, well, we know what a is. Now, we don't actually at the moment, because a is arbitrary. But a is some known value. And so a is just equal to a. So I'm going to let x0 be a, like I said before. x1 is just going to be a plus, well, I'm going to add on this b minus a over n quantity. x2, well, that's just x1 plus add on b minus a over n. But that's going to be a plus 2 times b minus a over n. And so on, I just keep repeating this process. And so x sub I, the ith iteration, is going to be a plus I times b minus a divided by n. And so that's telling us what each of these x sub i's are. And so it's just telling us where kind of these interval pieces actually are falling. What is the actual value? Now notice b minus a over n comes up a lot when we do this. So when I write this as delta x is just b minus a over n. Notice that it is how much we are changing in the x direction. We're doing b minus a over n. That's the distance between each of these pieces, which I'm just calling it delta x. Remember, delta x stands for change in x, and that's how much we're changing x by. And so it's just corresponding to what we've used delta x for in the past. And so now, if we're going to use rectangles, these are all the bases, but now we need the heights. Well, the heights, we can do it two ways. We can actually do it more than two ways, but we've done it two ways. We can take each of these endpoints and form the right-hand side. And so we can do like a right-hand side type of thing, in which case we'd be using f of x1, f of x2, f of x3, f of x4, and so on. And so if we do the right-hand side, what we see is when at f of x1 times delta x, because again, delta x is the width, f of x2 times delta x, and so on to f of x sub n times delta x. And so we could do the right-hand side like this, but we could also do the left-hand side like we were doing earlier. And so we could take the left-hand side and use that to form our rectangles, which the picture gets kind of crowded, so we're drawing them both. But we could use the left-hand side. And now if we use the left-hand side, we start with f of a, which is x0. So we have f of a, which is x0, times delta x, plus f of x1 times delta x, and so on, up to f of x sub n minus 1 times delta x. Now we only go to n minus 1 there because the last rectangle is off of x minus 1's height, where we used xn's height on the right-hand side. But both of these give us approximations with n rectangles. And the idea is, well, if we use more and more rectangles, these pieces are going to get smaller and smaller. So the amount that they are off is going to get smaller and smaller. And so as we take the limit as we go to infinity, we're actually going to get a perfect representation. And that hopefully is clear, because if you take some picture, and I take really, really small intervals, obviously I'm still going to be off by some, but notice I get off by a very small amount, and the smaller I make each of these intervals be off by, the smaller I make each interval, the smaller I'm kind of overlapping. So the smaller that my error gets. And so we define the area to literally just be the limit. Okay? And so, like I said, the area, which we're going to call A, of the region S that lies under the graph of the continuous function is the limit of the areas of the approximating rectangles. Okay, so going off of what we have done in the past, we're just literally saying here is that the area then is going to be the limit as n goes to infinity of r sub n. So it's the limit of these r sub n values, which is the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. And this is just making use of our sigma notation from before. That's why we talked about it before. You can see that this sum is clearly just the sum from I equals 1 to n of x sub I delta x. And this is the sum from I equals 1 to n of f of x sub I minus 1 times delta x. But we could also define it with the left-hand side, taking limit as n goes to infinity of L sub n, which is the limit as n goes to infinity, the sum from I equals 1 to n of f of x sub I minus 1 times delta x. So those are both appropriate definitions for this area. So we can use left-hand sums or right-hand sums, and these will be equal to each other. Now, a key thing to note here, which we're not going to go into all the details of why this is, this does depend on them being continuous. So if you take a function that's not continuous, these two limits might not be equal, and they might not exist. Okay, and so we can run into issues in that case. Okay, now the limit will always exist, and these two will always be equal if the function that we're looking at, if the function f of x that we're looking at is always equal, is always continuous. I didn't write down the continuous function f. But f is obviously the continuous function with how I've set it up. Okay? So what we want to do now is we want to actually compute the area that we were doing before. So we want to compute the area under the curve y equals x squared from 0 to 1. So we want to compute the area under y equals f of x, y equals x squared, I mean, from 0 to 1. Okay, so we've got our picture, we've got our function, goes from 0 to 1, and now we're going to actually compute this area. So we used rectangles before, and using rectangles before, we saw it looked kind of like it was going to 1/3. But now we're going to actually compute that. And to do so, we are going to use the right-hand side. It doesn't really matter if you use the left-hand side or right-hand side. I kind of prefer the right-hand side just because if you actually look at the formula, this piece is a little bit easier to do f of x sub I rather than f of x sub I minus 1. That is the only reason why I have a little bit more preference towards the right-hand side. It's just the formula looks slightly easier. But they both work. So the idea here is we have our function, y equals f of x is x squared. And what we want to do is we want to compute this area. And so the area is the limit as n goes to infinity of r sub n. Just as the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I times delta x. Well, we need to talk about what f of x sub I and delta x are. Remember what delta x is. Delta x is literally b minus a divided by n. But right now, we're going from 0 to 1. So b is 1 and a is 0. So this is 1 minus 0 divided by n. So we have 1 over n. Now, since we're taking the limit as n goes to infinity, n is not fixed. So n is just some value that we're changing. So 1 over n is delta x. And now we know what f of x is, but we need to talk about x sub I. We talked about this before, though. X sub I is literally a plus I delta x. Remember, that's what we found up here when we were looking at how to find these values. We were just taking a and then adding on one more change in x repeatedly. And for x sub I, we added on I times. And so we have I times delta x. Which a is 0, and delta x is 1 over n. So this is just going to be 0 plus I over n. So x sub I is going to be I over n. And now we plug those into our formula to find that what we're doing is we're taking the limit as n goes to infinity of the sum from I equals 1 to n of 1 over n squared times, or not 1 over n, I over n squared. I over n squared times 1 over n. And now we've computed limits like this before. We talked about this briefly in the sigma notation video. That's why we did that example in the sigma notation video, is computing those limits is literally just computing areas. So we want to do this limit now. So we have the limit. So n goes to infinity of the sum from I equals 1 to n. I squared over n squared times 1 over n. So this is the limit as n goes to infinity of, we're going to have the sum from I equals 1 to n of I squared over n cubed, which is this limit. So n goes to infinity of 1 over n cubed times the sum from I equals 1 to n of I squared. Remember that we can pull constants out of sums. And now we talked about before what the sum from I equals 1 to n of I squared is. If you don't remember, it's equal to n times n plus 1 times 2n plus 1 divided by 6. That formula can be helpful to memorize in Calculus 1. Sometimes you'll be given this and don't have to memorize it. Other professors will make you memorize it, so Just be aware that it is helpful to know those formulas. But we can now just plug that in for our sum. And so we have the limit as n goes to infinity of 1 over n cubed times n plus 1 times 2n plus 1, all divided by 6. Okay, and so that is what we are computing here. Notice we have an n on the top and n's on the bottom, so this is the limit. So n goes to infinity of n plus 1 times 2n plus 1 divided by 6n squared, just combining things. And so multiplying this out, we have the limit as n goes to infinity. On the top, we're going to have 2n squared plus 3n plus 1. And on the bottom, we have 6n squared. And so this then becomes the limit as n goes to infinity of, we're going to have 2n squared over 6n squared plus 3n over 6n squared plus 1 over 6n squared, just breaking it up into pieces. The n squareds cancel on the first one. We can cancel one of the n's on the second one and none of the n's on the third one. So we have the limit as n goes to infinity of 1/3 plus 1 over 2n plus 1 over 6n squared. But as n goes to infinity, 1 over 2n will go to 0, and 1 over 6n squared will go to 0. And so we're left with 1/3. And so that gives us that this limit of the right-hand sums is 1/3, which with how we defined area means that the area under this curve is indeed given by the value of 1/3. Now, one thing to be aware of is that in how we defined these areas, we specifically said we're using the left-hand or the right-hand side. In all reality, that doesn't really matter. Whether you use the left-hand side or the right-hand side, it doesn't actually change the final result. But in fact, you don't even have to pick them consistently. And so if we take some region here, we're going from A to B. If we divide this up into pieces, as we've done before, so this is S1, S2, S3, S4, and S5. It turns out if you pick any point in each of these intervals and use that, you will get the same answer. So let's say I pick this point for my rectangle in the first region. On the second one, I'm going to pick this point right here. The third one, I am going to use the left endpoint. On the fourth one, I'm going to use the right endpoint on 3. On 4, I'm going to use the left endpoint. Then I'm going to use the midpoint on 5. And now, this seems kind of weird. I've just picked these sort of randomly. But it turns out that as you take the limit as n goes to infinity, as long as you have some method of how you're picking these, you're going to end up getting the same answer in the end. And so this is the idea of sample points. And so the idea is, to make this a bit more general, is in finding the heights of the ith approximating rectangle okay, and so the ith just means we're just, picking one of the rectangles, and for finding its height for the ith approximating rectangle, we can pick any sample point x sub I star in the interval x sub I minus 1 to x sub I. And so this is the ith interval, and so you're picking any value in the ith interval to get the height. And so before we were picking the right endpoint or the left endpoint, but in reality you could pick any value in that interval and you'd be fine. And so that gives us what we're calling x sub I stars. And in this case, the area is given by the sum, the limit. It then goes to infinity of the sum from I equals 1 to n of f of x sub I star delta x. And so this is kind of the most general way that we could do this. It turns out if you have a continuous function, doesn't really matter what you pick in the interval as long as you pick something. That being said, it is usually easiest to just use the left endpoints or just use the right endpoints. If you do other things, you kind of open yourself up for a more challenging situation. So now let us look at another example. Okay, and so we're going to let A be the area of the region under the graph of f of x equals e to the minus x between x equals 0 and x equals 2. And what we want to do is we want to use right endpoints to find the expression for A. Okay, as a limit. So we want to figure out this area as a limit. We're not going to compute the limit. We actually won't have the techniques to compute the limit right now. And so first off, what we're saying here is A is 0 and B is 2, because we're going from 0 to 2. I wrote x squared here. I meant to say from x equals 0 to x equals 2. And so we have A equals 0 and B equals 2. And so delta x is b minus a over n, which in this case is 2 minus 0 over n. So we get 2 over n. So 2 over n is our delta x. So now we want to get our x sub i's. Well, x sub 1 is going to be 2 over n. X sub 2, we're going to add on one more of them, so it's going to be 4 over n. X sub 3 is 6 over n, and so on to xn. It's going to be 2n over n. In general, x sub I is going to be a, which is 0, so 0 plus I, times delta x, which is 2 over n. So x sub I is 2i over n. Okay, and so that is the general x sub I. And so our right-hand sum formula then is giving us that r sub n is equal to f of x sub 1 delta x plus f of x sub 2 delta x, and so on to f of x sub n times delta x, which, plugging things in, this is e to the negative x1 delta x plus e to the negative x2 delta x, and so on to e to the negative xn delta x, because f of x is e to the negative x. And this then is equal to e to the minus 2 over n times 2 over n, plus e to the minus 4 over n times 2 over n, and so on to e to the minus 2n over n times 2 over n. Just plugging in the x sub i's and delta x as 2 over n. And so now we can factor 2 over n out of everything. So we have 2 over n times e to the minus 2 over n plus e to the minus 4 over n, and so on to e plus e to the minus 2n over n. And so this is then equal to 2 over n times the sum from I equals 1 to n of e to the minus 2I over n. And so that then is R sub n, and we just want to take the limit of that. And so our area is the limit as n goes to infinity of 2 over n times the sum from I equals 1 to n of e to the minus 2I over n. Like I said, we do not have the techniques to compute that limit right now, but that would be giving us our limit. And so that is the idea for the area in this case. And then in the next video, we are going to talk about the distance problem. So I mentioned that at the beginning of this video. The next video will cover the distance problem.